Thank you. Can you hear me well? Okay. I'd like to thank the organizers very much for inviting me here. It's been very pleasant so far, and I'm looking forward to the whole week and the discussions we will have. So my lecture this week will be about the effective field theory approach to post-Newtonian gravity. And in the first lecture, I will more explain a bit what that is all about. And then in the next lecture, we'll go more into the actual calculations, how you can apply it to make predictions for gravitational waves. But so today, I more explain what is this effective field theory approach. And also how the post-Newtonian approximation fits into the overall picture of everything. All right. So just to set some notation, let me draw a picture of a binary system. So this is one object in the binary, say a black hole or a neutron star. And there's a companion over here, say. They have two masses, M1 and M2. And they are orbiting each other. So they are going around their common center of mass. But let's say if this guy is much heavier than the other one, then the small one is going in an ellipse around the bigger one. Then the distance of closest approach, that's the Parameswaran distance, right? Then there's a distance between the center of the ellipse and the focal point here. Let me call that, how do I call it? C bar. So that's the so-called linear eccentricity, right? So if it's 0, then basically you have a circle, and the eccentricity is just 0. The quantity that you would normally call eccentricity E is related to that by C bar divided by A, right? So that's how things overall look like. And A is the semi-major axis, which is basically the distance from the center to the Parameswaran point. Now, if now these two objects orbit around each other, they will emit gravitational waves. And the waveform, I suppose you've seen it several times, but let me still draw it here. The waveform more or less looks a bit like this. So you have some sinusoidal-like signal, but it increases in amplitude and frequency over time. That's because the system is emitting energy in the form of gravitational waves. So the two will move closer together, and the frequency will thus go up. And also, they will be moving more and more into the strong field regime. Overall, the dynamics will become more violent, and therefore also the amplitude of the gravitational wave goes up, just qualitatively, until they reach the point of maximum amplitude. That's usually when they start to merge. And after the two objects merge, you have a single object which is losing its perturbations, so to say, or it's ringing down. So that's the last part of the signal. So roughly speaking, we have an in spiral phase early on. Then here, there's a merger and the ring down. So that's how the gravitational waves look like that are emitted by the system. Now, if we want to predict the gravitational waves, there are several methods which one can apply to that. And predicting those gravitational waves is very important because in the process of analyzing the data that is measured by the detectors, one needs to compare the predicted signals with the measured signals. often the signals are also buried under noise. So then it gets even harder. But even if you can see the signal rather clearly in the data, you want to compare it to theoretical predictions, so you can figure out what were the masses of the source, or say the spins of the black holes. In the case of neutron stars, other properties like tidal deformabilities one wants to measure or at least get constraints on. And for that, it's really essential to make those predictions and to make them very precise. So there are now several methods to do so. One of them is just so-called numerical relativity. So in numerical relativity, you would be solving the Einstein equations on large supercomputers, right? So those are nonlinear partial differential equations, and solving them numerically is difficult, but it's possible. But what is particularly difficult is to solve them when the binary separation is very large. That's not because the numeric gets particularly hard, but it's just because the time steps that you use in the evolution become very small compared to the orbital timescale, right? So it just takes a long time to evolve even a single orbit when the binary is very far apart. So that means if we make a plot of where each of those methods work best, then basically we could say numerical relativity lies more in the right part of this, when, so to say, m is the total mass of the system and rp is the Prayush distance. It works best when the binary is close together, right? When the orbital separation is not too large. So this means I would put numerical relativity more or less here in that chart, where m is m1 plus m2. Now, what is the other axis here? So this is the mass ratio. So there's another slight problem with numerical efficiency if the mass ratio is too large, too disparate. Because then again, so to say, you have one large scale in the system, which is the mass of the heavy black hole, say, and the small scale, which is the mass of the small black hole that's orbiting it. Also, then it takes a lot of computational resources, even just to a single orbit, for similar reasons, right? So whenever you have two very disparate scales in the system, numerics becomes difficult. Right, so numerical relativity is would be somewhere over here. Now, there are other methods which help to fill in the remaining space here. And one of them is indeed the Post-Newtonian approximation. Let me abbreviate this with PN. By the way, is it too small, or should I write maybe bigger for people back? Bigger, okay, yeah, I'll try. Good. So the Post-Newtonian approximation would be somewhere over here, because the Post-Newtonian approximation is one where one assumes that the velocities of the binary are rather small compared to the speed of light. And that means also that the separation must be rather large, right? So if the two guys are orbiting at a close separation, they are moving very fast. If they are a large separation, they are slower. So the method of applicability is somewhere at large separation, at large Parameswaran distance. So that's good. So we have something which works, say, for comparable masses, one more for the in-spiral in this weak field regime and numerical relativity in the strong field regime. If one goes down here to very extreme mass ratios, one can apply another method, which I will call the small mass ratio approximation. Right. And there's yet another one, which is the so-called Post-Minkowskian approximation. Right. So these last three ones here, they are all approximations. So there's always some small parameter to expand in, whereas the first one is in some sense exact. It's an exact numerical approach. But of course, you also have a numerical error. Now, the last one is closely related also to scattering amplitudes. In the sense that it is possible to do calculations for binary systems using scattering amplitudes. But there usually one applies this post-Minkowskian approximation, because the post-Minkowskian approximation is just a weak field approximation. So you can apply it to scattering, but at arbitrarily large impact velocity or impact energy. So the post-Minkowskian approach usually, well, it requires a third dimension here, which indeed would be the eccentricity E. And the post-Minkowskian approximation can go all the way up to infinite eccentricity. So here would be infinity. Say here's eccentricity of 1. And here, let's say 0. Then the post-Minkowskian approximation can go all the way down here up to infinite eccentricity. So what that means is if you keep the periastron distance constant, but you increase your eccentricity, then you need to make the two black holes faster and faster, right? So they pass by each other without barely scattering. If you make the impact velocity a bit smaller, let's say, then the black holes will scatter at each other and get deflected more and more. Until, so to say, below an eccentricity of 1, you have a bound system, right? So that is the parameter space here. Now, the post-Newtonian approximation is also applicable somewhere around here. And likewise, the post-Minkowskian approximation can also be used over here, because it's just a weak field approximation, but not a slow motion approximation. But so to say, the post-Newtonian cannot go all the way up to here. So there's some kind of limit, let's say, up to where the post-Newtonian approximation here is valid. And after that, only the post-Minkowskian approximation can be used. Right. But in general, the point is that one needs the combination of several methods to make any predictions, right? Because we want to have the signal during the in-spiral, merger, and ring down, ideally. We want everything. And that means the binary is moving from here to here, roughly, right? From large separation to smaller and smaller separation until it merges. So one usually needs to combine several methods in order to get a full, complete waveform. The exception is kind of the small mass ratio approximation, which in principle could do everything on its own, so to say. But then one also needs waveform models with different mass ratios, right? The mass ratio is never exactly infinity. And if you go to intermediate mass ratios, also then maybe you want to combine several approaches together with a small mass ratio approximation. So one needs to combine several of those methods in general. And in this lecture, I will explain mostly what the post-Newtonian approximation is and how it works. So the PN approximation as I briefly said already, is a weak field and slow motion approximation. So if we have our binary here, at some separation R. So this, let me call this the orbit scale. Then so to say, that fixes one of the scales in the problem. There's another scale, which is just the scale of the bodies itself. Let me call that big R. Okay, let me make the big R a bit bigger also. So big R is roughly the size of the bodies. Small r is the scale of the orbit. But now there's a different scale in the system, which is fixed by the gravitational waves, right? So they will be going out, being emitted from the system. And the characteristic scale here is the wavelength. And now the point is, so to say, there's a small scale, which is big R, the size of a body. Then the next slightly bigger scale is the size of the orbit. And the gravitational wave scale, the length of the gravitational waves is even larger, right? So we have usually, we have a hierarchy of the scales, which goes like R is the smallest, then there comes the size of the orbit, and then the wavelength. However, of course, this doesn't have to be the case. When the two bodies are very close together, then the size of the orbit, the size of a body, and also the gravitational wavelengths are all comparable, right? So only when the orbit is at a large separation, you have this hierarchy of scales. Now, the point is that if this is true, then the PN approximation is possible. Right? So when you are in spiral regime, you have this separation of scales and you can do the PN approximation. And the expansion parameter is the following. Let me call that epsilon here. So you could say it's size of the orbit square divided by the wavelengths square. This is approximately the same as the velocity square divided by the speed of light square, because the wavelength, you can estimate it as speed of light times the size of the orbit divided by the velocity, right? So r divided by the velocity gives you roughly the orbital frequency. And if you multiply it by the speed of light, you get to the wavelength of the gravitational waves. And by virtue of Kepler's third law, the velocity is related to the separation in the following way. So you have gravitational constant times total mass divided by r, which is the velocity square. So this comes from Kepler's third law. Right, so this is the expansion parameter and how it relates to those other quantities here. The size of the body is not in there, so to say. But you see here we have the size of the orbit and the gravitational wavelength, and also the velocity in the binary. Okay, and one thing to remember is that one PN order here corresponds to 1/c², at least when you're looking more at the binary, at the orbital scale, right? Because at the orbital scale, what matters is the velocity and the orbital separation. And you see it always comes together with a factor of 1/c² here. So if you want to make your life a bit easier, you could just count factors in 1 / speed of light. And this corresponds to the PN counting parameter. It doesn't quite work at the level of the gravitational wave propagation, so to say. So there one has to be a bit more careful. But as long as you look at the orbit, you can just count powers of 1/c. And that's also what we are going to do here. Okay, so that kind of sets the overall stage for the PN approximation. And now you could just go ahead and expand the Einstein equations in this small parameter, and this will give you some approximation scheme and some results. But it had become more and more common recently to apply effective field theory techniques, which are particularly prominent also in quantum field theory and particle physics, to this problem, right? Because in particle physics, basically, you have very efficient tools to do perturbation theory, like Feynman diagrams and Feynman integrals. And we want to apply all those technologies to this problem and to this perturbative expansion in this epsilon here. And in order to do so, we want to embed this approximation scheme into an effective field theory framework or way of thinking. And yeah, I mean, this works quite well because we have a clear hierarchy of scales in the problem. And so we can build an effective field theory for this problem. What we will do is the following. We'll split the metric, or in general, we'll split the fields in the following way, according to the scales in the problem. So we say the metric is some flat spacetime metric, eta. So this, say it's a flat cosmos. So also this can be generalized later, of course, that one says the cosmological metric is not just flat, but there's something more going on because we have galaxies around, right? And the gravitational waves are interacting with the gravitational fields of galaxies. There's gravitational lensing of gravitational waves, etc. So there may be propagation effects, and one cannot really treat the cosmos as flat, but let's for now say it is. Then we have some modes in the gravitational field, which I will call H mu W for the wave scale, right? So this corresponds to the wave scale, everything that's at the scale lambda. And we have an H mu O for orbital scale. And there's an H mu B for the body scale. And I mean, in general, there might be more and more scales, of course, which are at lower and lower distance, right? Because also the body itself might be composed of something else. There's some physics going on inside the body, and gravitational fields generated at those scales, which would come further down here. And yeah, so the indices mu, as usual, run over 0, 1, 2, 3. And I'll use the mostly minus signature for these lectures. Now, let me draw a picture corresponding to that. So let's look at the gravitational field H, but not directly, but in Fourier domain. So let me put a tilde on top of it to denote that I'm going to Fourier domain. And let's plot it over the wave vector k. Then the way one could think about it is the following, that one has several modes here in this picture corresponding to the different scales in the problem. So we have, say, 1 over lambda regime in the Fourier domain, which corresponds to the wave zone here, to the wave regime. So here are the modes of the gravitational field corresponding to HW. So there would be some excitation of the gravitational field over here, let's say. Then there comes the next regime, which is the orbital scale. And we have the body scale, where there are some modes, and then maybe there's even more at lower scales, but also down here, things would in general continue, say, with some cosmological modes of the gravitational waves, of the gravitational fields. So here, as I said, that's the orbital scale, 1 over r. And here we have the body scale, and this is 1 over big R. And here, there's, so to say, everything at yet smaller scales. So say if you have a neutron star, then that would be described by quantum chromodynamics or something else. And for a black hole, there's not really anything until you reach the singularity. And then, so to say, there might be quantum gravity effects at some point. But there's always something at lower scales happening, right? Yeah? Yeah, I mean, so this is just qualitative. I mean, I cannot really prove that the amplitude goes up, but it's just that naively, I would expect that as soon as you go to a gravitational field at smaller and smaller distances, it goes stronger and stronger. But yeah, I mean, it doesn't have to be like that, but it's also not so important, right? And likewise, so to say, the gravitational waves usually have a field that is much, much smaller than the field at the orbital scale, right? But that's more because they are propagating and then they get a very low amplitude, for example, right? So, I mean, I think it's not wrong, at least for these three here. But here, I mean, I don't know. I mean, of course, there could be fields that the gravitational field wave encounters, which are much larger. It's quite possible. If you have a lensing of the gravitational field of a black hole, also, this would be larger, I think, than the gravitational wave itself. But the point is more that they are separated by different length scales. That's a more important point. Yeah. Are there other questions up to this point? All right. So now, in the effective field theory approach, the idea is, so to say, that one can integrate out all those pieces of the gravitational field, or the bunch of modes, bit by bit. So one starts basically with the lowest scales around here or around here. One integrates them out of the theory, and one gets an effective theory that's valid for everything that's at the lower scale, right? Or larger length scale. And then from here, one continues and integrates out, say, the gravitational field, the metric at the orbital scale, and then one gets the theory at the wave scale, etc. So that's the overall idea. So we now want to integrate out scales from the action. And we want to use quantum field theory methods to do so. Yeah. Yeah, so this, so this should be just the Fourier domain. So H tilde is just a normal Fourier transform. But so what do you? For H. Right. So I mean, but I mean the eta is basically just the Minkowski metric, right? Yeah. Yeah, I mean, I would say that H, I mean, you could just define it like this, right? I mean, it's also not so crucial here. It's just that in the path integral, it's easier to work with H, right? Because eta is more like a static background, if you want. Yeah. But yeah, I mean, I guess one could equivalently put the G here. It's just that you don't have a GW plus a G orbital, because then you're double counting the eta. So I mean, it's better to just put it out. But yeah, indeed. But I mean, so this shouldn't mean that those H's here are always smaller than eta. I think that's not required here. Yeah. All right. So yeah, so we want to go and integrate out smaller scales bit by bit. And also we are kind of assuming that the modes in Fourier domain are cleanly separated like this, which I mean may not always be exactly the case. I mean, the scales are still talking to each other, right? That's an important point. So this is really an idealized picture. All right. But now, once we have that, let me give you a bit of more intuition of this process of integrating out the scales. So in the classical physics regime, let's say, this integrating out scales is basically a coarse graining. So what that means is, say, for the example of granular matter, you could do some kind of averaging over the granular matter, and then you get to some continuum or fluid description, right? Okay. So this picture is also not so bad when integrating out the first piece, namely this body scale, as I will try to explain now. But I mean, this is mostly still a very classical approach and classical picture. So let's maybe briefly recap how such a coarse graining works. Yeah. Yeah. Though not quite. I mean, it depends a bit on the regime. So when you have the small mass ratio approximation, you would more expand in the ratio of the masses. But also then you have different scales in the system, right? You have a small scale of one of the black holes and then a larger scale of the other black hole. So the approach works a bit differently, but people are also trying to apply effective field theory methods and quantum field theory methods to the small mass ratio approximation. But it's harder, so to say, because the tools maybe from quantum field theory are not fully adapted to that problem. Or let's say the setup is a bit unusual for particle physics, right? So in particle physics, you usually look at a scattering and then you do a small weak field or a small coupling constant approximation. While when you have a small mass ratio system, basically you have a big black hole and you have, say, like the Kerr solution, like a fully nonlinear exact solution to the field equations, which you usually often don't have in quantum field theory. And you want to take that as a background. So you are not working in a flat background, but in a curved background already. And then you need to do perturbation theory in that background. Right, so it's a somewhat more unusual setup from the perspective of particle physics, but people are trying to work it out. I mean, you still have the separation of scales, but just not exactly this one that you have in the post-Newtonian approximation. But then the post-Newtonian approximation only works for the weak field in spiral, right? While the small mass ratio approximation works all the way into the strong field regime. Yeah. Where the one is? Yeah, so this should be here at the top. Sorry. Yeah. So I mean, it goes from 0 to 1, basically. Yes, exactly. And likewise here, I guess here there would be the 1. So to say when MO, well, I mean, should there be a 1? Well, I mean order 1, let's say, right? Yeah. So when this becomes order 1, basically the two objects merge. Yeah. Well, it does, but it doesn't, so to say, introduce an extra scale in this picture, right? So, I mean, we'll discuss this later, how, so to say, the rotation of the body will enter, but this is all already covered by the orbital scale, right? Or more precisely, when you integrate out the field of the body, you will get the spin as a parameter in the effective theory, and then you just go on with the calculation. Yeah. More questions up to here? Okay. Then let me explain a bit how the first step works. So yeah, I mean, one problem is that the first step, integrating out the body scale, in some sense, is already the most complicated, because inside the body, say inside the neutron star, you have strong gravitational fields, so you can barely do anything analytically, right? So in that sense, it's the most complicated thing if you want to do a first principles calculation. But what I will try to do is more take a more phenomenological approach, or just try to explain how the calculation could be done. and then, so to say, try to make an ansatz for the result, right? I will try to illustrate it in two different ways. I mean, one which is a bit more precise by looking at how you treat granular matter in classical physics. So let's say you have some granular matter made out of point masses. So this could be a gas also, right? And now you want to go to a continuum description of those point masses. Then usually what you do is you do an average, right? So let's say this is the spatial dimension, then you just average over a bunch of those particles to get to a continuum description. And this f is the function I use in the averaging. So this could be a Gaussian, for example. And what you can then define is an averaged density. So instead of working with point masses, so to say, you average over them, and then you have a continuous density. And the average density is just defined as usual. So you have an integral over all of your volume. You have your averaging function. So this could be a three-dimensional Gaussian also with a certain width. And you have the original density, so to say, the granular one. So this could be a sum of delta functions, for example. And I mean, this approach, for example, is also taken in classical electrodynamics. If you look at the Jackson book, he applies this, say, to point charges, right? You have a bunch of point charges or atoms or so, and then you define an averaging, and you go through the calculation. You get to Maxwell equations for macroscopic media. And that's basically an effective field theory construction, if you want, right? You go from one scale where you can isolate the individual charges in the material to a larger scale, an average scale, and then you get Maxwell's equations in media. Right, and now since this picture over there is more in the Fourier domain, let me also explain how this works in the Fourier domain. So in the effective field theory framework, one usually thinks more of the Fourier domain and of wavelengths, etc. So that's why it's maybe useful to do that. So in Fourier domain, again, let me put it just a tilde on the f, on the averaging function. You would still have something like this. So if you Fourier transform a Gaussian, you still have a Gaussian. And say the width of that Gaussian, that kind of defines a cutoff scale. So let me call that k cut for cutoff. So here, that's again on the x-axis, there's now the wave vector k. And this roughly is proportional to 1 over the cutoff in x space over here, right? So yeah, I mean, you average over a certain scale, right? Which you can call the cutoff scale. And now in Fourier domain, the averaging procedure is just a multiplication of your averaging function, or you could also call it a filter, let's say, with the Fourier transformed density or mass density, charge density, etc. Right? So you basically you do a low pass filter in Fourier domain, right? You let the small wave vectors or large scales through, and so to say, you filter out the small scales. Yeah, so that's how the averaging looks like in the Fourier domain. Now, if we apply that logic to the body scale, so it will look like the following. So we have, say, our neutron star or black hole. And now we could also think of applying an averaging or filter to it, roughly speaking. Right. And we have the size of the body, and we have the size of the cutoff, right? So more or less the width of the filter function, which we could also change and tune, of course. And now, roughly speaking, what happens is if we do that, say if we make the cutoff larger than the body, then so to say the body will just become a point particle, right? So you can think of it as looking at the system with a camera, for example, and you can zoom in and zoom out of the system. And if you zoom out a lot, so to say, then the pixel size, which is basically the cutoff size, once it becomes larger than the body, then your body will just be one pixel in your picture. So it will be a point particle, right? So if you take what is usually called the continuum limit, in which one makes basically the cutoff scale. What? No, okay. Yes, so, sorry. So what one does, so to say, is one first does the averaging, and then, so to say, one does a rescaling of the system where one takes basically the spatial, one rescales the spatial dimensions such that the cutoff goes to 0. That's called the continuum limit. And in that limit, so to say, you will obtain a point particle. Right. So, I mean, it's not enough just to average, because after averaging, I mean, you still have something of non-zero size, but you want to average, but then rescale your spatial dimensions such that the cutoff basically becomes 0. So it goes to 0. And then, so to say, your body will just be one pixel in the picture, and you have a point particle. But I mean, it's important to remember that physically, both the size of the body and so to say the cutoff are non-zero, right? And that's important because later on one often encounters divergences in the calculation, which are related to the fact that one approximately has taken the cutoff to 0, right? But physically, of course, that's not the case. It's just a mathematical idealization. Yeah. Both. Yeah. So for now, I'm more looking at one body, let's say. But yeah, in the end, I want to make both bodies point. And from there, I mean, one could already see that it's maybe not the best approximation for small mass ratio situations, right? Because one of the bodies is very large, and if you make both of them a point, then the approximation will only be applicable when the orbital scale is much larger than both of the bodies, right? Yeah, yeah. But yeah, I wanna do this for both bodies. Yes. So roughly speaking, we want to take both of the bodies as point masses or point particles. But yeah, as I said, I mean, it's very difficult to work this out in detail with the calculation, say to do the averaging really explicitly, because one is already in the strong field regime of gravity. So the only method that's available to even get this solution here is numerical methods, right? You can describe a neutron star. You can solve the Einstein equations for a single neutron star, but you have to do it numerically. And then you have a numerical solution, and then you can extract from that properties of the point particle. So that's the approach that's usually taken, and that works, right? So you can extract, of course, the mass quite easily by looking at the asymptotic field. You can also extract the angular momentum or spin of a neutron star or black hole by looking at the external field, and also higher multipole moments like the quadrupole moment of a neutron star, of a black hole, etc. So by looking at numerical, or in the case of black holes, analytical solutions, but exact solutions, you can extract the properties of the point particle, but you more do so with a matching procedure. You make an ansatz for the point particle, and then you match its properties to the full solution. Now, there's another approach to this integrating out of scales, which is given by the path integral. So I just also wanted to mention that, because this will be very important later when we want to integrate out the orbital scale. But in principle, I mean, you could also think of applying it to the body scale, but only in a more formal way. Yeah. Let's so to say both. Yeah. So one does a rescaling of all the length scales of your unit of measuring length, such that those go to 0. That's the idea. So yeah, if you change your unit of length measure, then both of them will go to 0. Yeah, exactly. Yeah. Yeah. No, it could also be slightly deformed. So in the tutorium, I mean, one discussion would be, or one exercise, let's say, would be exactly about this averaging to work it out in a bit more detail. And there, so to say, there's no assumption of spherical symmetry there, right? And then what one will get is a point particle, but with multiple moments, right? So basically, this approximation is doing, well, it's a bit convoluted way of explaining how the multipole approximation works. It's just that this connects better to what you can find in the literature about effective field theories, right? That you're integrating out modes in Fourier domain, you have a cutoff in Fourier domain. So this is more to make the connection between the normal multipole approximation that you have in Newtonian physics, say, and the effective field theory terminology. But also, I mean, it's applicable to electrodynamics when you derive Maxwell's equations in continuous media, etc. Right? So I guess the point is that the effective field theory way of thinking had been around already for a while, right? It's just that now you have a framework, a way of thinking about a hierarchy of scales and how to apply approximations to them that works for many, many different scenarios. And of course, you can apply it to Maxwell's equations in continuous media. You can apply it to multiple approximation of bodies, etc. Right? The way of thinking works in all those cases. Yeah. But yeah, so there will be more about this also in the tutorial. Yeah. Very good. Do you have more questions? Yeah. Yeah. How long is it? I have no. Okay. Good. Good. Yeah, the other method, which is a more common one of thinking about integrating out different modes and different scales, is with the path integral. So that's also where the name integrating out is coming from, right? Because you literally integrate, do the integrals for those modes in the gravitational field. Now, the path integral, let me briefly review that. With the path integral, you can compute in-out amplitudes, where so amplitudes are here in the sense of quantum mechanics or quantum field theory, right? So they are probability amplitudes. Or if you draw a picture for that, it would look the following. So let's take a very standard example of a screen with two holes in it. Right, so you have a screen, there are two holes in it, and you have some wave which can either pass through this hole or through that hole. And then here in the end, you have another screen where you observe the result of that scattering. So say you have a source for your waves somewhere here. So that would be, say, the initial state. Then basically your particle could go through here, or it could go through here. And then it somehow gets to the screen, say over here. And this is your final state. This is initial. And here it's the final one. Then the amplitude would be f into I. And using a path integral, you could write this as an integral. Say over all field configurations H. And the integrand is e to the power of I divided by h bar times s, the action. Right? So this is basically the path integral. So it's a formal integral over all field configurations. And the integrand is e to the I divided by h bar times the classical action. Now, what this means more in this context often is, or the first incarnations of the path integral were really that you integrate over all the paths that go from the initial point to the final point, right? So in quantum mechanics, the path integral is really an integral over path and not field configurations. And you kind of sum all the paths weighted by this factor e to the I times the action. And then you go through all the paths and sum them up. So to say, you integrate over them. And it doesn't really matter whether the path is classical or not, right? That's kind of the point. You just weight it by the action in this way. And the classical path will be the one where you have a stationary point in the integrand, right? So this is a highly fluctuating function. If the integrand is stationary, so you have delta s equal to 0, then that's the point where usually you expect the highest probability. And that's exactly the classical point. So that's one way to see how it fits to the classical limit, right? So that's where the exponent gets stationary. That's the classical path, the classical limit. But you really sum over all the possible paths, even the non-classical ones. And here you see, I mean, could go around the corner like this. This definitely is not a classical path, right? Classically, particles would only move along straight lines. So that's how you can compute it in quantum mechanics. And in field theory, instead of summing over all the possible paths from initial to final state, you sum over all the possible field configurations. Yeah. So this is really a very, let's say, degenerate high-dimensional integral. So you could think of this as basically an integral over all the fields at all the possible points, right? So you could discretize your space-time, and then you have an integral for each space-time point. But in reality, of course, you have a continuum. So this is a very non-trivial, high-dimensional, infinite-dimensional integral in practice, right? If you do lattice quantum field theory, basically you actually do discretize the space-time, and one can, in principle, perform the integral like this, right? And depending how many points you have in your lattice, then this will fix the dimension of the integral. And yeah, this will then, so to say, explore all the field configurations. So at each point, you integrate over all possible values of the field. Right. Now, that's a very nice formula still to work with, because what one can do now is, so to say, split the field into the different modes and then integrate out mode by mode in this path integral formula. So this thing here, one could write as an integral over the wave scale modes and an integral over the orbital modes and an integral over the body scale modes and so on. Yeah. So one could equivalently look at the Fourier domain modes instead of integrating over the field configurations in position space. And in Fourier domain, one could split up the integral really like this. Right. So if one does that, one will get the following. So we then have three integrals of right. First one over the body scale, then over the orbit scale O, and then over the wave scale. And the integrand is E over I h bar times the full action, whatever that may be. So that could just be gravity in the case of black holes, but it would be gravity plus QCD in the case of neutron stars, say. And now, sorry, let me put the integral signs here. Yeah, so one could, I mean, it doesn't matter at this point. So to say one could stay in the Fourier domain, but one could also then go back to the X domain. But yeah, strictly speaking, these would be in the Fourier domain. Now, what one can do is one computes this integral and then rewrites it again as an exponential, right? So we can write this as some constant. In general, there's always some constant in front. Times e to the I divided by h bar s. But of course, this is not the same as here, right? So this will now be our effective action. And let me also put a b over here because we have integrated out the body scale. And now we will do the same thing with the next scale, right? So we take the path integral, we integrate out the body scale modes, rewrite the result again as an e to the I divided by h bar times some action. And then, so to say, this we can call our effective action, where the body scale is integrated out. And now we do the same with the orbital scale. So again, we write it as some constant times e to the I divided by h bar. And then we have an effective action with the orbital scale integrated out. The orbital scale fields. And in principle, one could go on like this in any direction, smaller scales or larger scales, right? So this basically is a coarse graining process at the level of the action itself. Right? So this is very nice way of thinking about constructing effective theories, because this is super generic, right? As soon as you have an action to start one from, you could apply this process to get to actions at other scales, at larger scales, integrate out modes. I mean, it should correspond to the coarse graining process over there. It's somewhat more abstract. At the body scale level, this still is not very useful, because in practice, you cannot really do this integral, right? So again, we are kind of stuck here with making an ansatz again. But at the next scale, at the orbital scale, we have this small parameter epsilon, the Post-Newtonian counting parameter. And then, of course, we can solve the path integral, right? So we have something to expand in, and doing path integrals in a perturbative setting is perfectly fine. I mean, there are very efficient tools to do that. And in particular, this path integral where you integrate this and rewrite it as an exponential. So this is given by all the connected diagrams in the Feynman diagram approach, right? So this will also automatically do the exponentiation for you. So this is why this is so useful, in particular when you have a small parameter. Okay, but now before we do that, let's go back to integrating out 8b nu. So as I said, this is very difficult. Due to the strong gravitational fields that we have at that scale. So we cannot really do apply any approximation. But we can still do something. Namely, we now just make an ansatz for the result. And I've already motivated to you that one should end up with a point particle when integrating out the body scale field. So our effective action at the body scale will be the Einstein-Hilbert action still, right? So the action for the gravitational field basically is just the normal one. So we have the Einstein-Hilbert action. Then we also need a gauge fixing term. Otherwise, one cannot really do the path integral without the gauge fixing. And we have a point particle action for body 1 and a point particle action for body 2. And now this point particle action can also be rather complicated. And the approach would be to make an ansatz for it and then try to fix the unknowns in some way. But for now, so we get things going, let me just make the very, very simple ansatz. So we will just say that the point particle action is, well, yeah, it's an integral over the proper time. So we want to make this a covariant ansatz. And the first term is just a constant, right? Let's call this M1. And if this should have the dimension of a mass, you would need to put a C square here. But then there can be corrections to that. In the tutorial, yeah, as I said, you will work out this coarse-graining picture a bit more, and you will also see how some of those corrections will look like in Newtonian gravity. And later in the lectures, we'll also discuss those corrections in GR and how to make this ansatz, how to put in the spin of the bodies, etc. But for now, let's just stop here. So just take the point mass, the simplest model possible. And the corrections will then be of higher order in the multipolar approximation, which is the size of the body over the size of the orbit. Okay, so this will contain spin corrections and also tidal interactions. Okay. So yeah, the approach is basically making an ansatz, make it covariant or make it compatible with any symmetry you would expect to be there. And then, yeah, I mean, you will have some constants, coefficients like this M here. But in the terms that will follow, there will be more coefficients like that. Here, the M is very easy to interpret, right? It's just the mass of the body. But one still needs to answer the question which mass it is. And it turns out to be that this is the so-called ADM mass. And this one can basically fix through a matching procedure. Now, what that means is the following, basically. So in GR, there are several definitions of masses floating around. So one still needs to figure out which exact mass this is. And the way to fix this or to do the matching would be that, say, one takes this point particle with the point mass term, one computes the metric of it, and for instance, compares it to the Schwarzschild metric, right? Just asymptotically far away where the field is weak. And then one can read off from, say, the term going as 1 over r. It will depend on the ADM mass in the Schwarzschild case, and it will depend on this M1 in the approximate solution, and one can compare the two and so to say, see how the two masses are related. And maybe not surprisingly, this M1 here is just the mass parameter that appears in the Schwarzschild solution. For Kerr black holes, of course, this would be a little more subtle because there are already several masses around. There's an irreducible mass and there's the ADM mass. And in that case, this M would be the ADM mass. So the total energy of the spacetime. Right. So yeah, that's basically now how one sets up the point particle action. And we have this full action at the body scale that we can work with. And now the next step would be to integrate out the orbital scale modes, the orbital scale gravitational wave, gravitational fields modes, using this action as the input. And we can use the post-Newtonian approximation, the fact that this epsilon is small, to do that and to do this path integral with quantum field theory methods. Yeah. Now I don't know this. Yeah. Okay. Good. Then yeah, let me briefly start with that. So the first part will not be a lot of calculations, but one first needs to see how, say, the pieces in the calculation, namely in the Feynman diagrams, we have vertices, we have propagators. We need to see how exactly they scale, right? So that's the first thing we need to figure out, so that we know, so to say, which diagrams we need to compute at which post-Newtonian order. Yeah. Yeah, the binary system is not. Okay, yeah, so this is important. Thanks. So the matching is usually done for a single body, right? So the logic is, so to say, that this effective action for the point masses, I mean, it's valid universally, right? So you can look at a binary or triple system, but you can also look at one body individually. And this, as an effective action, should still be valid. So if you do the matching, you would want to make your life as simple as possible. So you look at a single object and try to match as many coefficients as possible just from a single object. Yeah. Yeah, so, okay, what I mean is that usually the matching is done for a single body, and then it's you can identify it with the ADM mass. Matching those constants in a binary, I mean, it's complicated. I don't even know if that makes sense, because also if you use a Bondi mass, it's only approximate, I guess, right? It's yeah. So yeah, so usually one wants to do the matching for a single body only to simplify things. Or tidal effects, maybe it's a little different, right? Because for tidal effects, that would mean you have to put an external field to the body. And in practice, I mean, it could be even easier to have a small test body creating that tidal fields. So there it depends a bit, but also there, probably it's easiest to, so to say, scatter a gravitational wave of the body, look which gravitation wave goes out and then extract the tidal properties from there. Right. So for the matching, you always want to set up things in the most simple way as possible. Any way that gets you to a value for those coefficients is fine, right? Once you match it, you fixed it, and it's valid. And then you can take the action, take two of them, and do a computation for a binary, right? So yeah, that's the logic here. Yeah. Okay. Yeah. So the next step would be we integrate out the orbital scale field. And for now, we neglect the gravitational wave scale piece of the field. We'll put it in back in later, but in general, one should keep it in the calculation as well as an external background field. But for simplicity, let's put it to 0 first. Now, what we have to do in order to get an idea of how different diagrams in the calculation scale is the following. So we look at the integrand of the path integral. So this e to the I effective action at the body scale. And if we do so, and we look at the gravitational piece of the action, we see that the prefactor of the field part, so that's basically the Einstein-Hilbert action. Where have I left this one? It's here. So it has a prefactor of c to the 4 divided by h bar g, right? So the h bar is just coming from here. So that's not part of the Einstein-Hilbert action, but it is in the exponent of the path integral. And the Einstein-Hilbert action itself has this kind of prefactor, right? And the point particle just has an 1 over h bar. I mean, there's the mass, but that's not so important at this point. I more want to look at the factors in C and G at this point. Now we can rescale our h mu. And we want to rescale it such that the propagators don't carry any factor of G or C or h bar. I mean, that's just a choice, so to say. One could choose not to do so, but often it's a bit easier to figure out the order of a diagram if the propagators don't scale with those constants. Now, the propagator part in the action is the one that's quadratic, right? And we have this prefactor over the whole action, in front of the whole action. So we want to rescale the fields by the square root of that. And then the quadratic piece of the action will not have any of those constants in front. Yeah. So we rescale this guy by square root of h bar g c to the 4. So that's the square root of the inverse of that. So in the piece of the action that's quadratic in h, then basically all those constants will go away, right? And that means then basically that there's no h bar, no c, no g in the propagator. And there's one more little thing that we can already know. Which is that if we have a field vertex now, so this would be a vertex, and now we have graviton propagators going out of that, say a number of n also. Then, since we did this rescaling over there, we know it will scale as h bar g divided by c to the 4 to the power of n, right? Because there's one factor for each of the h's. However, there's the overall factor of this in front of the whole action. So this means we have to put a -2 here for the vertices. So the vertices will scale like this. After the rescaling of the metric, the propagators will have no scaling in G or C or H bar. And the field vertices will scale like this. Yeah. There is a square. Oh, yes. Oh, very good. Yes. Square root H bar G. And here, yes, thank you. Very good. And for the world line vertices, it works in a similar way. So let me draw the world lines as a thick line. However, that's more for visualization purposes, right? Because we are not integrating out any degrees of freedoms on the world line. We're just integrating out over the metric. So this is just for visualization purposes. Nothing is propagating along those thick lines. They could carry a label 1 or 2, depending on the body that one looks at. But now there will be, in general, n graviton lines could be going out of them. And those scale as 1 over h bar, which is just coming from the overall factor. And then for each graviton, there's this factor here. However, the problem is that there might be additional factors of 1 over c. So here it might come from velocities, right? So the point particle action, when one expands it in the post-Newtonian approximation. So basically one expands the expression for the proper time in terms of coordinate time, one will get factors of velocity divided by c, for example. And here, basically, there might be time derivatives in the gravitational action, right? There are a lot of derivatives in the curvature, for example. Some of them might be time derivatives, and this will also give another factors of 1 over c. So the point is, from these rules, we can mostly read off the power in G only. But that's already something. So the first step would be to figure out up to which power in G we need to go, up to a given order, and then draw all the diagrams. And we can basically first figure out which kind of vertices are involved by the maximum power in G, and then we connect them all by the propagators, basically. So that would be the next step that we'll do in the next lecture tomorrow. Yeah, so thank you for your attention, and yeah.